Okay, so in today's class we shall be discussing about the principles of designing an S-box. Okay, so you have seen that the S-box plays a very key role to the security of the block cipher in talking in terms of linear and differential cryptanalysis. So today's class, the objective will be to understand some of the design criteria that the S-box must satisfy. Okay, so what we have seen essentially till now is that S-box is a table with elements which are being filled by entries which look to be quite random, right, some arbit values, but actually they are not random, and there is actually a quite deep science involved behind the design. Okay, so we will try to understand how the S-box is designed, or rather at least see some of the features or which the S-box should satisfy, some of the properties which S-box should satisfy. Okay, so first of all we will go straight to the question that what is an S-box. Okay, so what is an S-box? The S-box we have already seen essentially till now. It's a mapping, right? It's a Boolean mapping from m bits to n bits. So therefore it takes an m bit input and it produces an n bit output. Okay, so we can also call it an m cross n mapping, right? So therefore essentially you can imagine that all the n outputs that you produce essentially are individual Boolean functions. Okay, so they operate upon m Boolean inputs, and each of these component functions essentially is a map from m bits to 1 bit. Okay, so in other words, each component function is a Boolean function in m Boolean variables. Okay, so Boolean variables means the values can be 0 and 1, right? So therefore you see that each of the n component output bits can be either 0 or can be 1, right? So therefore we have to understand that how essentially these Boolean functions are designed. Okay, so we will try to address this issue in today's class. Okay, so that is the objective, right? So let's little bit go back into our what we know about Boolean functions, and we know that Boolean functions essentially means what? So if there are m input bits, I would like to obtain one corresponding output bit, right? So any Boolean function, you know, you can represent that in the form of a truth table, right? So the truth table was a canonical representation, which means that it was a unique kind of representation of a given Boolean function, right? So once given a Boolean function, I can always we know that by using we can express it using either min terms or max terms. So basically we know that we are quite familiar with the representation which is known as an AND OR representation, right? So that means that I am expressing something, a Boolean function, using AND and OR as my logic operations. Okay, so but when we talk about cryptography and actually cryptographic Boolean functions, then another representation is commonly used. It's known as the AND XOR form, okay, or the AND XOR expression. So it's called ANF form or the algebraic normal form. So how does an algebraic normal form look like? It looks like this. So therefore it's quite I mean, if you observe in this way, so for this plus, okay, in this case actually this plus does not mean OR, okay, it means an XOR. Okay, so all these operations are XOR operations, and you have got XORs and you also have got ANDs, like you see x1 and x2. Okay, so similarly you have got the final term as x1 and x2 and so on till xn. So all these coefficients, like coefficients running from a0, a1 till an, then you have got a12, a13, and similarly like you go on till an minus 1 comma n, and then finally for the final term like x1 to xn, you have got a1, 2 and so on till n. So therefore all these coefficients can take two values, right? It can either be 0 or it can either be 1, right? So how many such Boolean functions are possible? We can easily enumerate from this, because you know that there are how many possible Boolean functions? 2 to the power of n. Okay, so therefore you see that these Boolean functions essentially comprise of what we can actually represent all possible Boolean functions using this form, and also this form is a normal form. So what does it mean? It means that if I represent them in this, I mean if I would like to represent, I can obtain a unique representation, just like my truth table. This is an equivalent representation. Okay, and actually there are algorithms, quite easy algorithms, which takes a given truth table and can represent them in this particular form. So I am not going into those conversions, but you can easily do that. So maybe you can take it as a just a home exercise, and you can just try to find out some algorithms for doing that. Okay.
A1 to represent.
This just represents coefficient. So therefore, this can be values of. So this is just how the notation has been denoted, right? So when you are considering the term x1 into x2, then the corresponding coefficient is a1 comma 2. Okay. Similarly, when you are considering the coefficient of say xn minus 1 and xn, then I represent that by an minus 1 comma n. So that's only a notational thing. Okay. So therefore, these values can be either zeros and ones. Okay. So you note one thing, that we essentially will be addressing linear functions and non-linear functions. Okay. And also another function which is known as affine functions. So what is affine function? We have already seen how an affine function looks like. So you see that in this particular form of the equation, if we substitute all these values which have got and terms as zeros, like I mean to say the coefficients corresponding to these and terms are zeros, right? Then you have got a0 XORed with a1 x1 and so on till an xn. So apart from this, all the other terms go to 0. So what is the corresponding? So therefore, this equation which is remaining is actually an affine equation. Okay. So if this a0 value, that is a constant value, also goes to 0, then you have got only these terms, and then it actually becomes a linear equation, a linear function. Okay. So therefore, if apart from this, all other functions are non-linear, and you know why it's non-linear? It's non-linear with respect to the XOR operation. Okay. So we have addressed this in the context of linear cryptanalysis. We know what's a linear function and why it's called linear, and if it's non-linear, why it's non-linear. It's always with respect to a particular operation, right? So in this operation, in our case, is XOR. Okay. So how many possible linear functions are possible? We can also enumerate from this particular expression, this description, right? So you can work out how many linear functions are possible, how many non-linear functions are possible, and so on. Okay. So I can give a very simple example. So it's good to see some example. Like suppose you have got x1 and x2 as two variables, and let's consider the simple function of x1 or x2. Okay. So therefore, how will the truth table look like? 0 0 0 1 1 0 and 1 1. So apart from this, all the other terms will be ones. This is a simple OR function, right? So this particular thing we would like to express using a ANF form. Okay. So let's just try how we can represent this. So I call this function as y, and just see that y equal to x1 XORed x2 XORed with x1 x2. Does it work? So you see what is x1 XOR x2 XORed with x1 x2. Does it match? Right. So you see that I can actually represent. So if I mean this particular notation or this particular representation is known as the ANF representation. Okay. So therefore, there are actually algorithms, you can easily express them. I mean, given a AND OR form, you can actually convert that into an AND XOR form. Okay, and vice versa also. Okay. So therefore we have understood what is an ANF form. So why is an ANF form so important? The ANF form is important for various reasons. Okay. So one of the important reasons is that you can easily obtain the degree of a particular Boolean equation. Okay. So anyway, so we will go into this the various properties which a Boolean function, a cryptographic Boolean function, to satisfy one after the other. Okay. So consider a Boolean function which is a mapping from m bits to one particular bit. Okay. So let f essentially, which takes in an n bit number and convert that into a 0 1 bit, be a Boolean function. Okay. So therefore, this is a simple example of a Boolean function, and then we define something which is known as a binary sequence. Okay. So binary sequence essentially means I would like to represent them in the form of f alpha 0, f alpha 1, and so on till f alpha 2 power n minus 1. So this is, so therefore this particular notation is we know commonly as a truth table, right. So what does it mean? That I will take every possible assignments of my input and find out what is the corresponding output if the input is being sensitized by that particular value. Like for example, this Boolean function f, if I give an input of alpha 0, the corresponding output is f alpha 0, okay. And how many such possible inputs can I give? I can give 2 power n possible inputs, okay, and I stored them, store all the outputs in a table which is commonly known as a truth table, okay. So that's the definition of a truth table. So there is another quite closely associated term which is called the sequence of a Boolean function, okay. So what is a sequence? So the sequence is quite simple, I mean similar to a truth table, only thing is that each element is represented by -1 to the power of that particular element, like -1 to the power of f alpha 0, -1 to the power of f alpha 1, and so on till minus alpha to the power of -1 to the power of f alpha 2 to the power of n minus 1. So what you do is that you take the truth table elements and you raise each element to the power of -1, okay. So therefore what will be the sequence in this particular example? So if my for example, if the truth table elements are 0 1 1 1, then what will be my sequence look like? It will be -1 to the power of 0, -1 to the power of 1, -1 to the power of 1, and -1 to the power of 1, right. So therefore I will write this as 1 -1 -1 and -1, okay. So therefore in a sequence each of the elements can be either +1 or -1, okay. So that is how a sequence of a truth table is defined. Truth table of a sequence of a truth table for a given Boolean function is defined, okay. So then we will see certain criteria which a good Boolean function should satisfy, okay. See, as I told you that for all attacks the main objective was to find distinguishers, right, distinguishers from random mappings, okay. So we know that if you take a random function, then what you expect is the number of zeros and ones should be essentially equal, right. So one of the criteria which a Boolean function should satisfy, and it is quite obvious also, is that the number of zeros and ones should be same, right, and that is called the balancedness of a function, okay. So a balanced function is a Boolean function if its truth table has got equal number of zeros and ones, okay. So therefore we also note this term, we know this term called Hamming weight. So therefore if I have got a binary sequence, okay, so the Hamming weight of a binary sequence is the number of ones, right. So therefore you know that the number of ones and number of zeros for a given particular truth table should essentially will be identical, okay. So therefore if you have got a n-bit Boolean function, then how many number of ones are expected? 2 to the power of n by 2, so that is 2 power of n minus 1, right, that is the expected number of ones, okay. So then we define something which is called a scalar product of two sequences, okay. So what is a scalar product of two sequences? So we have defined what is a sequence. So therefore given a Boolean function f and g, we can define their sequences by these two symbols, okay. So one of them I call eta and the other one is say epsilon, okay. So now we define, so therefore if you take the scalar product, so you know what is scalar product defined as. So therefore this is the notation of the scalar product. Then you can see that this is equal to the number of cases when f and g are equal minus number of cases when f and g are not equal, okay. So all of you see that. So therefore this is what is the dot product or the scalar product of the two sequences, right. So whenever you see that f and g are both the same, then that will add up to this particular product, and when f and g are not the same, then we will actually subtract -1 from that, okay. Because you note that your sequence has got only two elements, right, it has got either +1 or it has got -1, right. So when they are not equal, then you have got 1 in one case and -1 in the other case, and when both of them are same, then you have got either 1 1 or -1 -1. So both the cases the product computes to +1, right. So therefore you have got either, so therefore this you can enumerate by the number of cases when f and g match minus number of cases when f and g do not match. Do you follow? Yes. Okay. So therefore, using this particular notation, we will define something which is called a nonlinearity. So we have all the time we have been talking about nonlinearity, right? But we have not really quantized what nonlinearity means. So I will take an example to at least address to you what is nonlinearity. I think after that this particular slide will make better sense. Okay. So take this example like x1, x2, and so we know that there are possible values like 0, 1, 1, 0 and 1, 1, and take the same example. So x1 or x2, and we will try to find out what is the corresponding nonlinearity of this Boolean function. Okay. So what is the truth table? We have seen 0, 1, 1 and 1. Okay. So the idea is that you find out all possible linear functions in these two variables x1 and x2. So what are the possible linear functions possible? One of them is 0, like all of them is 0. Okay. So the other one, the other possible linear functions could be x1 itself, okay, x2 itself, and x1 XORed with x2. Okay, so we are considering linearity with respect to the XOR operation, right? So what are the corresponding truth tables for this? 0, 0, 0, 0. For x1, it is equal to 0, 0, 1, 1. For x2, it is 0, 1, 0, 1. And for x1 XOR x2, it is 0, 1, 1 and 0. Okay. So these are my possible enumerations of the possible linear functions. Okay. Next, what I do is that I take this particular truth table and I take all the linear functions or linear possible linear functions, and I find out what is the Hamming distance of these truth tables with this Hamming with this truth table. Okay. So that's why we define the term Hamming distance. Okay. So what is the corresponding Hamming distance of these two truth tables? What is that? How many cases do they differ? That is the thing, right? So how many cases do they differ? They differ in 3 cases. Okay, so that is D1. I call them as say 3. Okay, how many cases? So how do I mean? What is this? How many cases does this value differ from this particular column?
1.
It differs in 1 case. Okay, how many cases this differs?
1.
Sure. Yeah, so it differs in 1 case. How many cases does this differ?
1.
Yeah, it is 1. Okay, so your nonlinearity is defined as the minimum of D1. Okay, so they call them D1, D2 and D3 and say D4. D1, comma D2, comma D3, comma D4. So in this case that is equal to 1. Okay, so that is the definition of nonlinearity. So which means that now we can generalize this, right? So therefore, if you have got an n variable Boolean function, then you obtain all possible linear approximations, enumerate their truth tables and find out the distances. Okay, and out of them the minimum distance corresponds to the nonlinearity of the Boolean function. Okay, so you can note certain interesting things, like for example, if you take two linear functions, how many cases do they differ? It's always half the possible number of cases. So you see that there are 4 zeros and there are 2 differences, like, so in 2 cases they differ. Similarly, if you take these 2 linear functions, how many cases do they differ? It also differs in 2 cases. Okay, you take these 2 things, it also differs in 1 case here and 1 case here, so 2 cases. So all possible linear functions will differ in 2 power n minus 1 cases. Okay, so so actually we will find that a linear function, okay, and a nonlinear function will the distance, so what we are essentially considered is about the distance, right? So you will find that the distance is never equal to 2 power n minus 1, but it is always less than 2 power n minus 1. Okay, so only 2 linear functions differ in 2 power n minus 1 cases. Okay, but a nonlinear function will actually differ in less than none. So it's you can just assume this as if the linear functions form a space. Okay, so form various axes, and your nonlinear functions come somewhere in between. So therefore designing a nonlinear function is quite tricky. So if you make it far away from one particular linear function, it may fall close to the other linear function. Okay, but what you have to ensure is that the nonlinear function maintains quite a safe distance from all possible linear functions, right? So therefore our idea will be essentially, or rather our objective will be to maximize this nonlinearity. So we have to maximize this particular metric called nonlinearity. Okay, so how do we do that? But before we go into that, let us define generally what nonlinearity means. So, a nonlinearity of a Boolean function can be defined as the distance between the function and the set of all affine functions, but actually it is a minimum distance. Okay. So, therefore, you take f and you find out all possible affine functions, and I denote them by say g, and then you find out the distances with corresponding between them, and you denote the minimum of them or assign the minimum of them to your nonlinearity. Okay. So, nonlinearity is defined in this way. So, you see that nf is equal to minimum of d from f comma g, where g belongs to an, where an is the set of all affine functions over sigma n. So, sigma n means over n. So, therefore, it is an alphabet which is formed using n particular letters, okay, n particular symbols. Okay. So, forget the notation, but the idea is as simple as that. Okay. So, now you can try to understand why your df comma g is equal. So, what we are essentially concerned is with the distance of f with g, right. So, your distance with f comma g will be equal to 2 power n minus 1 minus half of eta comma epsilon. Okay. So, that follows from the definition of eta, definition of this particular dot product. Okay. So, I will leave it to you as an exercise to think why. Okay. But it follows straight away from the definition. Okay. So, therefore, if you know this, then defining nonlinearity becomes quite simple, because in that case nonlinearity becomes equal to 2 power n minus 1 minus half of this distance, right, and what we are interested is in making this distance minimum. So, what we will, so if we make the distance minimum, then we will make this particular scalar product as maximum. Okay. So, therefore, we write here maximum, and that is how it is defined. So, therefore, you see that what we observed intuitively, that the nonlinearity is always less than 2 power n minus 1. Okay. It is minus half of something. So, therefore, this term is actually a positive term. So, you will find that this is nonlinearity is always less than 2 power n minus 1. Okay. So, therefore, you can just give a thought that why it works. Any idea why it's okay, why it's correct, or shall I show it to you? Okay, so I will just give a hint, okay, and leave the complete the entire thing to leave the entire completing the proof to you. So, how was this defined? This was defined as number of cases when f is equal to g minus number of cases when f is not equal to g. So, now what we are interested is in number of cases when f is not equal to g, right. So, how can you express this in terms of this? It is equal to 2 power n minus number of cases when f is not equal to g. So, you have also got minus number of cases when f is not equal to g. So, you have basically got 2 power n minus 2 times number of cases when f is not equal to g. Okay. So, now you can actually rearrange this, because this is what you are interested in, right. You are interested in the distance between f and g, right. So, you are interested in the distance means you are interested in finding out this value. So, now you can just rearrange this and you will obtain that corresponding expression. Okay. So, now there is actually, just we will address this, that there is a very nice combinatorial tool called Hadamard matrices, through which you can actually enumerate or compactly represent all possible linear functions. Okay. So, therefore, if you see the definition of Hadamard matrices, you will see that the definition of Hadamard matrices works like this. You take H0 equal to 1, okay, and your H2 or rather H1 is defined as H1, H1, H1 and minus H1. So, what does it mean? It means 1, 1, 1 and minus 1. Okay. Similarly, you can also write H2. So, what will be H2 will be equal to 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, and you take the negative of this minus 1, minus 1, minus 1 and plus 1. Okay. So, why are we doing all these things? So, you see that Hadamard matrix has got a nice property. The property is that each of the rows, okay, So if you take each of the rows, then they denote the sequence of a, so if you are considering for example h1, then each of the rows will denote the sequence of a one variable Boolean function. Okay, so what is a one variable Boolean function possible? It can be either 0 or say x. Okay, so what is the corresponding sequence for 0? So if you consider a one variable Boolean function, okay, so what are the possible Boolean functions, what are the possible linear functions possible? It is either 0 or x. Okay, so what are the sequences possible? What are the possible sequences? It is either 1 1, okay, or it's 0 1. So what is the corresponding sequence for 0 1 is minus 1 1 minus 1. Okay, so 1 minus 1. So you see that precisely that is what your Hadamard matrix gives. It gives you 1 1 and 1 minus 1. Similarly, you see that for, you can extend that to H2 also. Okay, so the first one represents all possible. So therefore you see 1 1 1 1. So that represents the linear function 0. Okay, so next one is 1 minus 1 1 minus 1. So that is x1 for example. Let's, okay, what about this 1 1 minus 1 minus 1? So that's another variable, say x2. Okay, what about this 1 minus 1 minus 1 1? So that is x1 XORed with x2. So you see that you can form all two variable functions, two variable linear functions in this fashion. Okay, so therefore if I am able to find out or recursively express Hn, okay, in terms of Hn minus 1, then essentially each of the rows of the matrix Hn denote linear functions of n variables. Okay, the sequences of the linear functions of n variables. Okay, so what you have to do is essentially, if you have to obtain the corresponding, so therefore this is a very compact expression. So therefore if I want the corresponding linear expression for a given row, then what I have to do is that I have to take the corresponding binary representation of this. So therefore if I know that 1, for example 1 minus 1 1 minus 1 is my sequence, okay, then I can obtain the binary sequence from this, and the binary sequence would have been 0 1 0 and 1. Okay, and then I have got my variable list as, say, so I have got my corresponding variable list. So therefore what is the variable list? It is, so therefore if I take the dot product of this with the corresponding Boolean function, then I can obtain from this, that is my Boolean function is equal to x1. Okay, similarly I could have obtained that my, for this particular row it is equal to x2, and for this one it is equal to x1 XORed x2. Okay, so given the Hadamard matrix, from there I can obtain all possible linear functions. Okay, so therefore if you are told to generate all possible linear functions, then that is a nice recursive way of doing that. Okay, using this combinatorial tool. So now we are addressing the issue of nonlinearity. So you see that if there is, so there are some properties which we will just address, but we will leave the proof, but just for this timing just try to understand, I mean that it works. Okay, try to basically understand the insight. So it says that if a Boolean function fx is balanced, then so is fxb XORed with a. So a is an n bit vector and b is an n cross n 0 1 invertible matrix. So it means that if you have got an f function who has got a certain amount of nonlinearity, then doing an affine mapping in the inputs does not really make any change to the nonlinearity. Okay, so if you do an affine mapping to the inputs, the input variables x, using a invertible matrix, that is if this particular matrix B is invertible, and if you take this and if you do this operation, then still then the nonlinearity does not change. Okay, and so therefore what it says is that the nonlinearity of f and g are the same. So therefore nonlinearity really does not change through operations like this. But our S box should also satisfy another very important criteria, which is known as the strict avalanche criteria. But I think I have told somewhere what is meant by avalanche effect. So it means that if I change only one bit of the input, half of the output gets changed. Okay, so but thing is that formally we will try to define it. So what it says is that if there is a Boolean function fx, okay, and you define a vector called alpha whose weight is 1. So what does it mean? That only one bit is changed. Okay, So if you take x XOR alpha, so if its weight of alpha is 1, means it's basically a binary string in which only one of them is 1, the rest are zeros, right? So if you take x XOR alpha, so you see that in x XOR alpha and x, how many bits are changed? Only one bit is flipped, right? So this particular function, that is fx XOR alpha, is actually a balanced function. So that is the criteria of strict avalanche criteria. Okay. So it says that if there is a function, say for example fx, okay, and there is a function called fx XOR alpha, okay. So let's try to understand why only one bit is changed. So you take for example x as say x1, x2 and x3, okay, and your alpha as say 0, 1, 0. So what does x XOR alpha represent as? It is equal to x1, x2 XORed with 1 and x3. So you know from the properties of XOR that x2 XORed 1 means what? Complement of x2, right? So therefore you can represent this as x1 comma x2 complement comma x3. So you see that from this x, between this x and this x XOR alpha, there is only one bit which has been changed, and the idea is that fx XORed with fx XORed with alpha should be a balanced function, okay, should essentially should be still balanced, okay. And what we say is that there is also another way of representing this, so we call this as strict avalanche criteria, or often referred as SAC, okay, and we also says that it satisfies propagation criteria, something which is called a propagation criteria of order 1. Okay, order 1, why? Because the weight of alpha was equal to 1, okay. So the weight of alpha was equal to 1 in this case, right. So similarly you can understand, since I have said propagation criteria of order 1, I can also have propagation criteria for order 2. So what does it mean? I will just make the weight of alpha to be 2 and check for a similar property, okay. See, idea is that we are always trying to find out distinguishers from a random mapping, okay. So in a random mapping, if you change one bit of the input, you expect to get half of the output bits to get changed, right. So therefore this idea, what we are trying to do as a designer is try to maintain that all the property looks seemingly random, okay, trying various kind of tests and ensuring that really the function really looks like random, okay. So you see that when we define something which is called fx XOR alpha and say that the weight of alpha is 1, we say that the S box or the Boolean function satisfied what is known as the strict avalanche criteria. But higher order SACs are also possible when more than one input bits change. So both the SAC and the higher order SAC together make something which is called the propagation criteria, okay. So you see that can you see that where this propagation criteria can be useful in terms of linear and differential cryptanalysis? Immediately you can see that if you can maintain all these things, okay, then you essentially get a good differential property, because what you are doing here is basically subjecting the input to a differential, various kind of differentials, okay. So remember your differential distribution table, right. So therefore what did you do in your differential distribution table? You are subjecting the input to differentials, means what? You are considering various cases where you have given a differential to the input and we are checking that what is the possible output differential, right. So basically what you are doing is that you are taking one instance of the cipher or the S box and applying an input and checking its output and maintaining a differential, say alpha, and giving an input say x XOR alpha and again obtaining the output, and then you are obtaining what is the corresponding differential between fx and fx XOR alpha, okay. And if you can show that half of the cases, I mean it's a uniform distribution, then you will get a distribution table which is seemingly quite strong, right, which you really cannot maybe exploit so much for doing a differential attack, okay. So if you see that the previous study of nonlinearity was helping to overcome linear cryptanalysis, whereas this particular study is helping to somewhat protect against differential cryptanalysis, okay. So therefore given any Boolean function, we can actually make certain transformations and make it satisfy SAC, Okay, so what it says is consider a Boolean function fx and consider a nonlinear singular matrix, say 0 1 matrix of dimension n cross n. Okay, so what it says that if for each row of the matrix A, if this property satisfies, that is if x XOR with fx XOR gamma is balanced, where gamma is a row of the matrix A, then actually gx, which is equal to fx A, satisfies the sac. Okay, so do you see that why it's true? So also it's quite trivial if you follow the definition of sac. Okay, so let's see what it says. So it says that gx is equal to fx A satisfies sac. Okay, so we have to try to understand why it does so, right? So if we claim that gx satisfies sac, then what is the property that gx should satisfy? The given any alpha such that the weight of alpha is equal to 1, gx XORed with gx XOR alpha should be balanced, right? So what is gx? This means that fx A XORed with alpha A should be balanced, right? Instead of x, we have written x XOR alpha. Okay, so you see that what it means is fx A XORed with fx A XORed with alpha A should be balanced. Okay, and what is the property that you have? Okay, first of all, what is this x A XORed with alpha A? What is alpha A? So given any matrix A, okay, I define that A. Suppose A has got various rows like gamma 1. So suppose A is a matrix, you have got gamma 2, and similarly you have got say some gamma n rows. Okay, so what does alpha A represent? So remember that alpha has got weight of only 1. Okay, so what does it represent? What does alpha A mean?
Column matrix of 1.
Column or row? It means, so for example, you can just imagine that alpha is equal to 1 0 and so on 0. Okay, so what does alpha A represent? First row. Yeah, you are having alpha at the beginning and then A, right? So you have got the first row. Okay, so you have got gamma 1 here, right? Only one row, which is gamma 1, right? So what we are basically saying is that fx A, okay, XORed with fx A XORed with gamma 1 is balanced, right? And what was my design criteria? The design criteria was the fx XORed with fx XOR gamma is balanced. Another thing is important here is that this non-singularity property of the matrix. Why? Because what we have showed here is that fx A XORed with fx A XORed gamma 1 is balanced. Okay, and in order to ensure that this particular function fx A, if this, therefore if this matrix A is a non-singular matrix, okay, then this function will look exactly like the fx XOR gamma function, right? So if this function A is a non-singular matrix, then fx A and fx will behave in the identical way. There will be a one-to-one relation between both, right? So therefore, what you see is that if the condition is that if there is a non-singular matrix of dimension n cross n, and such that if for each row of the matrix A, if fx XOR gamma is balanced, okay, then gx equal to fx A satisfies the strict avalanche criteria. So we will just see one example in order to understand. So consider like x1 into x2 XORed with x3, which does not satisfy sac. Why? Just consider this example. Say alpha is equal to 0 0 1. So if we address this, if we obtain fx and I would like to obtain fx XORed with alpha, then what does it mean? I am not actually flipping x1 x2, but only flipping x3. Okay, so what does it become? It becomes x1 x2 XORed x3 XORed with 1, right? So if I now take the XOR between these two, I obtain 1, and which is not a balanced function. Do you see this? Okay, so therefore what I am saying is that fx is equal to x1 x2 XORed with x3. Okay, so consider alpha is equal to 0 0 and 1. So what is fx XORed with alpha? What is x XOR alpha? First of all, it is equal to x1 comma x2 comma x3 bar, right? So therefore that means that fx XOR alpha is x1 x2 XORed with x3 bar. So what does it mean? It is equal to x1 x2 XORed with x3 XORed with 1. I can write in this fashion. So now if you take fx XORed with fx XORed alpha, then what do you obtain? You obtain only 1, right? Because this part and this part gets cancelled. Okay. So now is this function a balanced function? No, because everything is 1, right? So therefore it does not satisfy the strict avalanche criteria. So we will see how we can make it satisfy strict avalanche criteria. Okay. So which means that we have to find out that particular matrix A, right? And here is an example. So without going into how to find, we will see that it works. Like you take A, where A is equal to 1 0 0 0 1 0 1 1 1. So what you have to do is that you have to find out E1, E2 and E3 such that fx XORed with fx XORed E1 is balanced, fx XORed E2 is balanced, and fx XORed with E3 is also balanced. So therefore here are some examples, E1, E2 and E3, and you note that all these rows or rather all these vectors are also linearly independent. Why is that important? Because we would also like to make the matrix A as a non-singular matrix. Okay, it should be an invertible matrix, right? It should have full rank. So therefore this matrix A essentially will look like this, and now you can check actually that Gx and define is like fxa will actually satisfy the strict avalanche criteria. Okay, so which means that if you make this transformation of the input variables x using this particular function, or rather using this particular matrix transformation, then this composed function or transform function will actually satisfy the strict avalanche criteria. Okay, so which means that if there is a particular Boolean function which does not satisfy the strict avalanche criteria, you can actually make it satisfy the strict avalanche criteria. And note another thing, that what you have done is that you have just taken x and multiplied that with an invertible matrix. Okay, therefore by my previous discussion, the nonlinearity of the function fx and fxa are actually the same. Okay, so therefore this particular transformation fxa does not disturb the nonlinearity of fx. So therefore without disturbing the nonlinearity of f, okay, you can actually satisfy the strict avalanche criteria also. Okay, so therefore if you know how to make a good nonlinear function which does not satisfy the strict avalanche criteria, after that you can actually make it satisfy strict avalanche criteria without disturbing the nonlinearity. Okay, do you follow that? Okay, so therefore these are some things which you can just keep in your mind, that for any n variable Boolean function, actually there is an upper bound to what the nonlinearity can be. Okay, so we will not prove this, but actually you can show the nonlinearity of any n variable Boolean function is actually lesser than 2 power n minus 1 minus 2 power n by 2 minus 1. Okay, and this works when n is even. Okay, so you see that n by 2 has to be an integer. Okay, and these functions are sometimes referred to as something which is called bent function. Okay, so these are called bent functions, and actually it can be shown that they satisfy the propagation criteria for all values of alpha, for all orders. Okay, but there is a problem with bent functions also. The problem is that it is actually an unbalanced function. So what does it mean? The number of zeros and ones are not the same. Can you say why? Okay, so so therefore these bent functions has got a nonlinearity of the maximal value. So therefore the nonlinearity of a bent function is actually equal to 2 power n minus 1 minus 2 power n by 2 minus 1. Okay, for all other cases it is lesser than that, right? So therefore the nonlinearity of a bent function is actually equal to 2 power n minus 1 minus 2 power n by 2 minus 1. Okay, so now can we relate to the fact that why it's an unbalanced function? Okay, so we'll just give a second to it, I will come back to it. Okay, so therefore this is an example of a Benn function. So you can take like x, so there are 4 variables x1, x2, x3 and x4. You just take fx is equal to x1 into x2 XORed with x3 x4. Okay, so this is an example of a Benn function in 4 variables. So what does it, so if it's a Benn function, what do you expect the nonlinearity of this to be equal to? 2 power 4 minus 1 minus 2 power 4 by 2 minus 1. So what is that equal to? How much does it work to? To 6. So we can check that all 4 variable Boolean functions actually will have a nonlinearity which is not a Benn function, will have a nonlinearity which is less than that. Okay. So there are some again properties, like if you take an f which is a Benn function, then so is f XORed with affine function. So if I take this and I XOR that with x1 XORed x2 or something like that, then it still, the nonlinearity does not change. Okay. Similarly, you can also see that for any non-singular binary matrix A, and if you do a similar kind of transformation to your inputs, then it still remains bent. Okay, the bentness does not change. So now I again come back to that problem, that again that why Benn functions are not balanced. Okay, so you can see that since Benn functions maintain a nonlinearity of at least 2 power n minus 1 minus 2 power n by 2 minus 1. So therefore, if I consider the distance from the all zero function, still then the distance should be 2 power n minus 1 plus, plus 2 power n by 2 minus 1, right? So therefore, the number of zeros in a balanced function is how much? 2 power n minus 1, right? So therefore, you see that the number of ones is actually equal to 2, is actually more than 2 power n minus 1 plus 2 by n by 2 minus 1. Okay. So why have I written a minus also here? Because actually what I am considering is that all one function also. So if we maintain that, if we look for both the functions, then actually you can ensure that you are not, anyway you are not able to obtain a number, you are not able to maintain the number of zeros or number of ones to equal to 2 power n minus 1. Okay, so that is not possible. So therefore, Benn functions are not balanced. That is the idea. Okay, although it maintains high amount of nonlinearity, but they are not balanced. Okay, yeah, I'll just. Okay, so therefore, this is an idea. So which I've already told you. So, so you can actually what you can do is that you can actually create balanced nonlinear functions. So therefore, I'm not really going into this. What it just says is that you can take some linear functions and you can start concatenating them. Okay, so you can just see this, and you will obtain that if you take say 2 power n minus k variable linear functions where k is greater than n by 2 and start concatenate the linear truth tables, then you will obtain an n cross k mapping which is nonlinear. So therefore, you can just take it as an exercise and just try to work out. And you can just prove also that the nonlinearity of this will be actually greater than 2 power n minus 1 minus 2 power k minus 1. It will also be balanced, and it can be made to satisfy the strict avalanche criteria also. Okay, so therefore if the question is the S box which you design good against linear cryptanalysis and differential cryptanalysis. Okay, so not only are the component functions good, but they have to satisfy high nonlinearity, like satisfy propagation criteria, etc. But also the problem is that their non-zero linear combinations also should satisfy these properties. So therefore, it's a quite challenging problem to design a good S box. Okay, so I will just conclude with this, that S box designing is quite complex, although you have to satisfy so many things, and then also finally what you can ensure you can end up is that this leaks informations in the form of some side channels and things like that. So therefore, it can happen that although you do so much mathematics, you can actually break these ciphers in minutes even after all the hard work. Okay, so and then there are other classes of attacks called algebraic attacks which I have not really touched into. So actually it's quite hard to design a good S box. Okay, so therefore I just conclude with this, that these are the properties which would satisfy balancedness, nonlinearity, and also strict avalanche criteria, and also high algebraic degree. That is, the number of AND products in your algebraic normal form should also be high. Okay, so you can take this as an exercise, that is, you can enumerate 8 distinct linear functions in 5 variables: x1, x2, x3, x4 and x5. So you can see, you can just choose 8 distinct linear functions in 5 variables. Okay, so you just take 5 variables and form 8 possible linear functions, and then concatenate their truth tables to obtain an 8 input 5 output function. So you can just see that why it works. Okay, therefore you can just take these functions, linear functions, and you start concatenating their truth tables. Okay, so then you store the resultant mapping as an 8 cross 5 S box, like what we have seen for DES, for example, and other S boxes. So the question is that what is the nonlinearity of your S box and does it satisfy strict avalanche criteria? If not, then modify the function to do so. Okay. So you can take this as an exercise, and along with your previous submission which is still pending, like the DES S box, you also submit this as an exercise. Okay. So these are some of the references that I have followed. Sebary's paper is quite interesting, you can read that, and then there is also Nyberg's paper which you can read. Okay. So next day we will talk about modes of operation of block ciphers.